Now let's see some additional chord properties in a circle. So today's session is about the chord and the angle subtended by the chord at a point. It can be the center of the circle or at any circumference of the circle. So today's session, angle subtended by a chord at a point. So let's see what exactly we can understand through angle subtended by the chord before we understand the properties connected. What do we mean by angle subtended by the chord? So let's take a circle to understand the concept more better through the geometrical means. Suppose I take a circle and I take a chord. So for this circle, my chord is AB. In this case, we understand the angle subtended by the chord to be, say for example, by the chord at a point. Angle subtended by the chord at a point implies if I take a circle with the chord AB out here, then let me take a point P on the circle. Now let's see what is the angle subtended by this chord with respect to the point P for the given circle. Angle subtended by the chord at a point P. So let's understand the concept through this circle diagram. So as we have the chord AB out here and the point P, I understand that this chord makes an angle with point P. We understand the endpoints of A and B for the chord make some angle with the point P. To some extent, let's see how it makes an angle with the point P. The left end of the chord AB joins with P, and the right point of the chord AB also joins point P in a manner that it subtends an angle, and this is called the subtended angle made by the chord AB. So here this angle is called angle subtended by the chord AB out here. AB, and this angle is being subtended converging up to the point P. So this refers to the angle subtended by the chord AB with respect to the point P. Chord AB at point P is how we understand angle subtended by the chord AB. If I take, say, for one more chord LM, so here is the chord LM, and here let me say there's a point Q. Then angle subtended by the chord LM with respect to the point P is similarly understood as the endpoint, the first endpoint L connected with the point, and the second endpoint M connected with the point, and then this refers to the angle subtended by the chord LM at point Q. This is the angle subtended by the chord AB at point P, and this is the angle subtended by the chord LM at point Q. Is how we understand the angle subtended by the chord with respect to the point. It's also very important to note that, say for example, I have a circle in which I have a chord AB. Say I have a point P out here. So let's see if the angle which I make on this diagram is the angle subtended by the chord AB at P. So let me just join this and let me just join this. Now let's see the difference between the angle as made by the chord AB with P and the angle made by certain distance in the line AB with point P. I clearly see that this angle is not subtended till the end of the right end of the point on the chord, but it is exactly just before the line or the chord AB. So clearly I understand that the rule for angle subtended by the chord with the point is that both the end points of the chord must subtend an angle such that we get a subtended angle of the chord. But since this gets subtended with the point, this does not get subtended with the point, therefore I say this is not the angle subtended. This is not the angle subtended by chord AB This is not the angle subtended by chord AB at point P, because this region is left over, since this region is left over, is how I understand the angle subtended by the chord at point, any point. It can be on the circle or other way. Angle subtended by the chord at a point for the given circle. Now that we have understood the definition of angle subtended by the chord at a point through the geometrical understanding of the circle, let's see some extended properties connected with angle subtension. So the first property which connects the chord and the angle subtended by the chord is as follows. So here my session is angle subtended by equal chords at a point. So let's see how the equal chords subtend an angle. So the property here says that two chords, here is the property statement, two chords which are equal in length subtend equal angles at the center of its circle. This is how the property comes. So the first property which connects angle subtended by equal chords at a point states that two chords which are equal in length subtend equal angles at the center of its circle. So let's see this through the geometrical circle diagram. Imagine I take a circle. Now the property says that if I take two chords which are equal in length, so let me take chord AB and CD which are equal in length. So I take the chord AB and I take the chord CD, provided they are equal in length. So with the first condition that the chords are equal in length, I have chosen the chord AB and the chord CD which are equal in length. That is, AB equals CD is the first condition which I take into existence. Chord AB equals chord CD. Now the property says that when I take the case of two equal chords, then the angle subtended by each of the chords will also be equal at its center. So suppose I have my center out here, then the angle subtended at the center by chord AB, and say this angle is some theta 1, and the angle subtended by the chord CD, say this is the chord CD, and the angle subtended at its center O is theta 2. Then clearly the property says that for equal chords which are equal in length, the angle subtended at its center must be equal. Therefore, implies for equal chords AB equal to chord CD implies the angles subtended at its center being theta 1 and theta 2 must be equal, is how we understand the property. Two chords of equal length subtend equal angles at its center of the given circle, is how the property holds for any circle and any equal chords taken into consideration. Property number 1, connecting angle subtended by equal chords at a point are equal, is how we come with the property. Now that we have seen the angle subtended by a chord at a point, let's see the relation between the length of the chord and its respective angle subtended at the circle, center, or any of its circumference. This session is about finding the relation between length of the chord and angle subtended. Relation between subtended angle and length of chord and its length of chord. So let's see how we can relate the subtended angle and its length of chord. So let's take a circle and understand the concept through the investigation of the length of the chord and its subtended angle. So here is the circle, and here, say for example, I take a chord AB, and here I have the center. Let me take another chord CD. Then clearly there are two subtended angles made by chord AB and chord CD. Say the chord AB subtends an angle at the center of the circle. This being the center, subtends an angle, say theta 1. There's another chord CD which is bigger in length, as clearly we can see that chord AB is smaller than chord CD and chord CD is bigger than chord AB. Therefore, the angle subtended by this chord CD with the center of the circle at the center, this. So we see that this angle is theta 2. So angle subtended by the chord AB at the center of the circle is theta 1, and the angle subtended by the chord CD at the center of the circle is theta 2. So we have two angles. Let's see the relation between the two angles. So here, since length of chord AB is smaller than the length of chord CD. Therefore, I clearly see that this makes a smaller angle and this makes a bigger angle, smaller than the length of chord CD. Therefore, chord AB makes smaller or subtends smaller angle at center O of the circle, and chord CD being bigger, chord CD subtends a larger angle at center O, is how we understand bigger the chord or bigger the length of the chord, the bigger is the angle subtended at its center. So here we come with the conclusion that the size of the angle subtended by the chord at its center of circle depends on the length of the chord. Is how I conclude the size of the angle subtended by the chord at its center of circle depends on the length of the chord. Bigger the length of the chord, bigger is the angle subtended at its center. Smaller the chord, smaller is the angle subtended at its center. So clearly I have here theta 1 is smaller than theta 2 because chord AB is smaller than chord CD. Longer the chord, longer is the angle. Smaller the chord, smaller is the angle. Is how I conclude the session. Now that we have seen a property connecting angles subtended by equal chords at a point, subtended by equal chords at a point, we have seen that if two chords are of equal length, then they subtend equal angles at the center of the circle. Now what would be the converse? Will the converse hold true for the same property? If I say that the two chords subtend an equal angle at the center, will the chords be of equal length? Is the reverse way of understanding the converse of the property which we have seen. So let's see the converse of the previous property connecting angles subtended by equal chords at a point. So here my question in the converse is, will the chords which subtend equal angles at the center, equal angles at the center of the circle be of equal lengths? Is the question which we are going to investigate through the converse. So here I have the investigative question which says, will the chords which subtend equal angles at the center of the circle be of equal lengths? The answer is yes. Two chords which subtend equal angles at the center of the circle must be of equal length. We can just try with geometrical ruler and the compass through which we can investigate the property. If I take a circle, if I take two chords which subtend equal angles at the center of the circle being O. I have the chord AB and the chord CD which subtend equal angles. Now, since they subtend equal angles, it is assumed in circle property that the side opposite to those angles must be equal. So, because these two are equally subtended angles at the center of the circle O, therefore, by converse, the two chords must be equal. That is, since chords AB and CD out here subtend equal angles at the center O of the circle, therefore the two chords must be of equal lengths, is how I understand the property. The two chords must be of equal length, provided they subtend equal angles at the center of the circle. So proudly I can say converse holds true. That's how we understand converse holds true for angle subtended by equal chords at a point. Now that we have discussed about the chord properties connecting angle subtended by the chord at its center or at its circumference of the circle given. Now let's see some additional properties connecting the chords. This session is about the property number 2 of the chord properties connected with the circle. So this property 2 mainly refers to the perpendicular line connecting with the chord, or how they are geometrically connected to each other. So let's see how a perpendicular line drawn through a center of the circle to the chord makes some new interesting geometrical properties coming into existence out here. So here the property says that the perpendicular here is the property number 2, which says that perpendicular distance, the perpendicular from the center of the circle to the chord bisects the chord. Is how we understand the property. The property says the perpendicular from the center of the circle up to the chord bisects the chord. So this is one interesting property which is identified in investigating a chord through its perpendicular distance, which is passing through circle. So let's see how it bisects the chord. So here I take a circle, I take a chord. So here AB is my chord connected with endpoints A and B on the circle. Now let's take the center of the circle. Here is the center of the circle. Now the property says the perpendicular from the center of the circle to the chord bisects the chord. So from center of circle, I drop a perpendicular. So here I have a perpendicular, say CD, out here. So this perpendicular CD bisects the chord AB. That is exactly, it passes through the midpoint. So when I understand this, when I drop a perpendicular from the center of circle to the chord AB, the foot of the perpendicular exactly lands at the middle point between equal distances. So here we have the property which says the perpendicular, when dropped from center of circle to the chord, exactly lands in the middle, that is exactly bisects the chord AB. Is how we understand. C is center of circle, CD is perpendicular, from center of circle C to chord AB. So CD is perpendicular distance from center of circle C to chord AB, and D is foot of perpendicular. So here I have center of circle, perpendicular distance from center to the chord AB, and D is foot of perpendicular. So the property says AD must be equal to DB, or CD bisects AB, is how we understand the learning outcome connecting the perpendicular from center of circle to the chord AB. They are equal, or CD bisects AB. This is always true when a line passing through center is perpendicular to the chord AB. Bisecting property of a chord. Now that we have seen the property connecting the perpendicular line which bisects the chord, let's see if the converse of the same property holds. Today's session is about the converse of the perpendicular property. So let's investigate the converse. So my converse question comes out to be, will the perpendicular line, or will the line passing through center of circle and bisecting the chord be perpendicular to that chord, is my question out here. So the question here is, will the line passing through center of circle and bisecting the chord be perpendicular to that chord? So this is what is the center of attraction in the converse. So let's see if it makes perpendicular. This is the converse of the previous statement. Perpendicular line passing through center bisects the chord. But what if a chord passing through center and bisecting the chord, will it make the line to be perpendicular to the chord? Is what is the investigation in the converse. So let's see if this holds true. Here is a circle. Now I have the center of the circle. Let me take a chord AB. So here is chord AB and here is the center of the circle. And the line passing through the center of the circle is in such a manner that if I take a line passing through the center of the circle, then such a way that it bisects the chord here. So here it cuts at D. This cuts at D. Now here, let me take the line L which passes through center. So here, L is the line passing through center C L is the line passing through center C of the circle and bisecting the chord AB, that is exactly cutting the chord at midpoint D. Therefore, AD equals DB, or D is midpoint of AB. Here is the chord AB. Now, the converse says that this line must be perpendicular to the chord. So, the answer to my question is yes. If a line passes through center of circle and bisects the chord AB, then the line must be perpendicular to the chord AB, is how we understand the converse. Therefore, that implies CD or line L is perpendicular to line AB, or you can also say CD is perpendicular to AB, is how we understand the property connecting the line and the chord. Line is perpendicular to the chord is how we understand the properties connecting the circle. So converse holds. Is how we understand. The converse holds true for the property connecting the perpendicular line with the chord passing through center of circle. Now that we have discussed the chord properties connecting the circle, now comes the concept of connecting a chord and a point, connecting a circle and a point. So this session is about investigating the number of circles which can be drawn through a point, or 2 points, or 3 points taken into consideration. Initially, to start with, number of circles which can be drawn through a unique point or 1 point. So today's session, chord, circle connecting the points. Circles passing through a point. So let's investigate, or before that we try to understand what do we mean by circle passing through a point. So let's see the circles passing through only one unique point. For example, I take a point P. So here I have a point P through which I would like to draw the circles. So for example, I have a circle which passes through point P. I can equally have another circle which passes through the same point P. I can also have another point, another circle which can pass through the same point. So like this, I see there are infinitely many circles which I can draw through those points. So what does this give? An indication. So here is circle 1, circle 2, circle 3 and circle 4 passing through the point P. So this gives me a clear idea that there are infinitely many circles which can be made to pass through one fixed point. So in this case, we understand that circles C1, C2, C3 and C4 pass through the same point P. So my learning outcome in this case is that infinitely many circles, of course of different sizes, not of the same size, many circles pass through a fixed point in the plane. So here my fixed point being P. So in this case, my fixed point is P, is how we understand. So my learning outcome here is infinitely many circles pass through a fixed point in the plane. Is how I understand infinitely many circles passing through only one fixed point, point P. Now that we have discussed about the number of circles which are possible to be drawn passing through a fixed point P, what happens if I take more than one point, that is 2 points on the plane? So my investigation in this session is about investigating the number of circles which are made to pass or which can be made to pass through 2 points in the plane. So this session connected with circles passing through 2 fixed points in a plane. Circles passing through 2 fixed points in a plane. So here let's investigate by taking 2 fixed points in the plane. Suppose I take 2 fixed points out here. So let's see how we can draw the different circles through this plane. Now with these 2 points, I have a circle which is made to pass through. So here I have a circle which passes through these 2 points. Similarly, I have another circle which passes through these 2 points. Next, let me take, yes, this is one more circle which is made to pass. And next, we have this. So here I find that for 2 points, say P and Q, which are fixed in the plane, there are infinitely many circles which can be drawn through those fixed points. Taken with, this is circle 1, this is circle 2, circle 3, circle 4, etc. So like this we can draw with different curvature or radius of curvature the different sets of sizes of circles, but passing through the fixed points P and Q. So here P, Q are fixed points in the plane, and C1, C2, C3, C4, etc. are the circles through P and Q. So what do we make the learning outcome here? Just like in the previous case, I make the learning outcome that there are infinitely many circles which can be drawn passing through the fixed points P and Q in the plane. So here my learning outcome infinitely many circles can be drawn passing through two fixed points in the plane is how I make the learning outcome. Two infinitely many circles can be drawn passing through two fixed points in the plane. The same property for one fixed point in the plane or for two fixed points in the plane, there are infinitely many circles which can be drawn through them. Now let's try to extend our investigation through 3 points taken in the plane. How many circles can I draw if I have 3 fixed points in the plane? Is what is the investigation connected with number of circles and the fixed points in the plane. So this session is about circles passing through three points. So let's see for 3 points taken into consideration. So here we clearly have a property in the statement which says that there is one and only one circle which passes through the given three non-collinear in the plane. So here the property is restricted to a finite number. That is, there is only one and only one circle which can pass through the given three non-collinear points in the plane. The condition is for non-collinear points taken in the plane. That is, if I have three non-collinear points in the plane which are fixed, then the theorem says that there is only one circle which can pass through these three non-collinear points. Is how we understand the property. A, B, C are non-collinear points where only one circle can be drawn. I cannot draw any other circle which can pass through all the 3 points. It is impossible to draw any other second circle passing through these 3 non-collinear points. Therefore, for the points A, B, C are non-collinear points. So here A, B, C are non-collinear points, and only one circle can be possibly drawn passing through A, B, and C. Is how I understand the circle connecting 3 points. For one point, infinitely many circles can be drawn passing through that one point. For 2 points, infinitely many circles can be drawn passing through those 2 points. But for 3 points taken in the plane A, B, and C, which are non-collinear, there is only one circle which can be drawn passing through A, B, and C. So my statement says there is one and only one circle which passes through the given 3 non-collinear points in the plane. Circles connecting 3 points. Now that we have seen the property connecting 3 points, that there is only one and only one circle which can pass through 3 non-collinear points. Now the question is, what if the points are collinear? So today's investigation is about finding the possible number of circles which can pass through the 3 collinear points. Three collinear points. So let's see, if I take 3 collinear points, how many circles can be drawn passing through all 3 points. Say my 3 points are A, B, and C, which are in the straight line. Collinearity in the sense they are in the straight line. So I have the points A, B, and C which are collinear. If I see that any circle I draw either through these 2 points does not pass through the third point, any circle passing through these 2 does not pass through this, and hence I have 0, or I cannot draw any circle passing through all the 3 collinear points. As the best I can draw is this, or the best I can draw is this. I clearly understand that for collinear points, ABC no circle can be drawn passing through all three points A, B, C. It is impossible to draw a circle passing through all 3 points. So my learning outcome in this case is it is impossible to draw a circle passing through all 3 collinear points. Passing through all 3 collinear points is how I make the learning outcome. It is impossible to draw a circle passing through all 3 collinear points. If the points A, B, C are collinear, there are no circles which can be drawn passing through all those 3 collinear points. For non-collinear points, there is only one circle which can be drawn passing through all 3 points. For collinear points, 0 circles. For 1 point, infinitely many circles. For 2 points, infinitely many circles. Is how we conclude the different possible cases taken into consideration. 3 collinear points taken in this case with no circle can be drawn.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.